Right. Uh, let's start maybe.
Okay. Well, sorry. Okay. Yes. So last time, we considered the Fox-Artin arc X, which was wild in one point, and we took a tubular neighborhood of it, and we got a 3-cell B, and we took its boundary, and that was a sphere S. So this is X, and this is S. And this was a sphere wild in one point, and both of its complementary domain were open 3 cells. And I think we didn't get time. Well, I didn't complete the construction that B or X are cellular. So I guess I'll start with this this time. So I suggest to see that it's cellular. I suggest to take the idea was as follows: was we take square neighborhoods VI of the wild point, such that Vn minus 1 intersect X looks like the diagram that I have. So it's a union of 3 arcs, Sn, Rn, and Hn. And I write capital S, capital R, capital H for small tubular neighborhoods of these arcs. So the picture looks like this. And also we have the other picture that I have basically represents the following. If we take the intersection of the complement of Vn, then we get a handle. Here it's denoted in white, and a tame arc. And similarly, Hn, An are tubular neighborhoods. Okay. Yes, so the problem was that if we naively fill this handle, then we create another handle, and we can't show that the arc is cellular. So to do this, well, we consider an isotopy to a point where everything is nice. So we have a family of isotopies, which basically just unwind the arc around the handle. So on the left side is the start point, and on the right side is the end point. And on the right, we can very easily fill the handle without intersecting the image of the arc, the tame arc under the isotopy. And then we would like to go back. And we need to be careful when we go back because we want, sorry, yes.
Could you please explain this isotopy once more? I didn't follow.
Okay, well, if you want this arc, An, I can view it as like a finite union of segments, yes? So this isotopy is contraction along each segment.
So what is it an isotopy of? What do isotope?
Oh, so it's like the whole of, so isotope R3, so that by contracting the arc An, so its identity, the isotopy that I choose is the identity on Vn and Hn, and then I contract An, and it's a homeomorphism on the complement.
Uh, uh, on the right, you have this yellow bar.
Yes,
It is the image of a n, is
yes,
it?
it's the image of AN, F1 AN. That's it.
Okay.
Yeah.
Mhm.
So
Thank
we
you.
take it to a nice position, and then we fill Cn. And then we would like to take it back, but we need to be careful when we take it back. I suppose that we consider the following family G and T of isotopes going the other way. Oh, right. Before, yeah, I forgot to mention, I have some notations. Right, so I say let Xn is equal to the union Hn with the arc and Vn. So yeah, so on the right is Xn, and Bn is the ball on the right, Cn union Fn of Xn. And this is the endpoint of the isotopy. And so this is a ball. And basically the cellular balls which we'll be considering will be these. So we take them back. Okay.
Sorry, how do you attach that yellow screen to the yellow bar?
I don't attach it to the yellow bar. I attach it to the handle.
Uh,
So this is a cube, for example, 0. I can choose Hn to be like, I don't know. So this is a cube, for example, 0, 1 over 2 to the n. And I attach it just like normally along the handle.
but then it looks like this Bn is not a ball because it seems to have a handle. This
I
yellow
filled the
bar.
handle. I filled the handle with Cn. No.
Okay, but when you so what is the intersection of the yellow bar and the yellow screen?
The
Is
yellow
it?
bar,
Uh-huh.
0. There's no intersection. I just drew it badly. Maybe
Okay. Okay.
like it's in 3D. So the yellow bar is slightly in front of the yellow screen.
Okay. Okay. I see.
Yeah. Sorry. Maybe my drawing is a bit misleading, but
Thank you.
yeah. Yeah. So they don't intersect. Okay. So yeah. So then Bn is a ball, and we would like to take it back to original arc. So the idea is to have the following conditions. So this is condition number 1 when we take it back. We would like Gn of Cn to be a subset of Vn minus 1 Vn. For example, for T in 0. So this is the picture number 1. So we protrude this, and the arc AN is the red, is the red segment. It kind of goes along. So CN forms a sort of hat, and then we extend it. So this was Hn minus 1. So so for the second condition, we would like so that's this is number 2. Number 3. And then and this is number 3. So in number 3, we see that the cube forms a hat over itself. But if we're careful, we always keep some fixed distance between them. Then it should be fine. It will still remain a ball. And then the last one, well, I don't draw this because it's quite complicated, but it's just we continue going along an minus 1. So an minus 1 is the arc that kind of comes out here, that's tame. And it's this was a tubular neighborhood of it. So we can continue this process. For example, if we pick an to be tubular neighborhoods of radius 1/4 to the n minus 1, then it works. Okay, so and notice that well, while we said this for Cn, the conditions 1 to 4 apply for Cn, then they also apply for An. We can satisfy them simultaneously for Cn and An. An is the red arc, and Cn is the cube, which forms a hat over the arc. Right. So yeah. So then the balls we want are these, and well, by construction we have. So then the intersection of xn is equal to the intersection of en, which is what we wanted.
But it seems that these balls are not, they don't lie one inside another, do they?
Yeah, they do, because if you see, look, each ball lies inside an minus 1, condition number 4. And before that, it lies, like everything before lies in so so condition number 4 says that at the end, the ball will lie in this arc. And before this, it lies first in here, and then in this handle. So this is the handle, this hn minus 1, it lies in the previous, and hn minus 1 is part of the previous ball because we filled it like this. If you want, I have another picture. I think I sent it a while ago. So they look like this. I don't know if it's visible.
Okay, it seems right. Mm-hmm.
Okay, yeah. Ну, все понятно, нужно что-то по-русски повторить. Окей, тогда двигаемся вперед. Okay, yeah, and so I think this construction actually, if we're careful, we can generalize it to any arc that's locally polyhedral modulo 1 point. So we would take the idea would be to take tubular neighborhoods. Would be to take a ball around the wild point. This would intersect the arc in a finite number of handles plus a tame arc. We would isotope to a standard point, fill the handles, and revert back. Right. Yes. So now I'd like to talk about some stuff about cellular sets. We have the following proposition. So let F be a map from the disk to itself. That's one-to-one on the boundary. It doesn't necessarily have to be surjective. And there's a unique inverse. There's a unique point F such that the pre-image is bigger than 1. Then the claim is, so this is called an inverse set. So Y satisfying this property is called an inverse set. The claim is that this is cellular. Well, since Y is one-to-one on the boundary, and then we can suppose that it's contained in the interior of the image. So we can take a ball around it. So if this is the image, the blue is the image. So this is the first disk. This is the first disk, and this is the image disk. And the idea is the following. We would like to perform, there's a map S epsilon that is kind of a radial contraction according to this graph. So it's the identity on a ball of radius epsilon over 2. And then we squeeze very hard so that the image lies inside the ball of epsilon. And again, we can say identity close to the boundary. Right, and so this gives us a map sigma epsilon. So if this is the pre-image set. That will allow us to parameterize neighborhoods of the set X. And sigma epsilon is defined in the following way. Is X when X is in X, and we conjugate by F the squeeze. Well, by the supposition F was injective everywhere else but on X, right? Y is the unique inverse set. We required it to be one-to-one on the boundary, so we can take a neighborhood. Well, it's identity on X. So sigma is indeed well defined, and it's continuous. So it's a homeomorphism onto its image. Injective continuous map between compact Hausdorff spaces is a homeomorphism onto its image. So we have parameterized a neighborhood of X. So then we can complete the proof by just picking a sequence of epsilons which tends to 0. and then define the balls as and these will be the cellular set.
Why cannot you just take so you have one point in the range in the target which has a non-trivial point inverse. So why cannot you just take its disk neighborhoods, epsilon neighborhoods, round bolts around this point, and take their preimages? Wouldn't those be both?
But it's not, I don't understand why F inverse is a homomorph. I mean, this is basically what I'm doing. But I just added this condition so that it's a homeomorphism. So if we just take the pre-image, then we get something that looks like this on X. So by doing this, I take the diagonal.
What are these blue sets in your picture?
So the blue sets on the right are the image of the disk, right? So I didn't suppose that it's surjective. And then the second one is what I get by squeezing to get it inside a ball of radius epsilon. And then
So are you assuming that the boundary goes into the boundary?
No.
Oh, I see.
I said it's one-to-one on the boundary.
I see.
Yeah.
But then you just have the image of the entire disk, and that's your first blue set, isn't it?
Yes, that's that's this set.
Okay, I see. I now see. Then you take some ball around this point inside of this image.
Yeah, and I squeeze very hard.
Squeeze. But what is the second blue set then?
That's the image of the.
Can you say again?
That's the image of the big blue. So I want to squeeze so that the image is inside, is very small. And then I take its pre-image under F. And I claim that this parametrizes neighborhoods of the cellular set or of the inverse set. We don't know it's cellular yet.
But why? Okay. So why not just take balls around this point, which lie inside of this image? So we know that this point is the only point where. So if you look at this white disk, then
which one? This
one, yes. Which was there, yes. So it has some pre-image, and on the pre-image of this white disk, the map is surjective, and it is non-injective just in the pre-image of the one point.
Yes.
So why cannot you just take smaller round disks around that point and take their pre-images?
Ну, прообразы этих сфер, они-то будут сферами, но они могут же не ограничивать n-мерный диск, да, потому что они могут ограничивать там что-то, они могут вот в левое пространство дико вложены. И неизвестно, что они там ограничивают.
Но у них есть двойной воротник, they are bicolored.
Ну так это воротник-то да, но Филипп-то это лемма к теореме о воротнике.
Да,
Там нельзя использовать, запрещено. А так-то да.
Okay. Okay, I see. We cannot do this because they could be wild. But then how do you overcome this problem? Could you explain again, please?
Well, I take the ball and I want a homeomorphism of the ball itself, and I will squeeze very hard on this ball so that it lies inside the image.
Okay.
And then I revert back.
So are you taking the preimage of this a small blue set?
So I claim that this map sigma epsilon is a homeomorphism, right? It's a map from the disk to itself, and it's a homeomorphism, but its image parametrizes the sets like balls, which the cellular set which parametrizes the X.
So how do you define this map again?
So here.
Okay, I see. Thank you.
Okay. So then if we have a map between balls and a unique inverse set, then that inverse set is cellular.
Извините, я так припоминаю, что это вот как частный случай критерия сжимаемости бинго.
Да.
У нас вот один прообраз, он сжимается. Отсюда, значит, вытекает, что эти первое пространство и второе, что они гомеоморфны.
Да, я вот хотел про это сказать сейчас. Ну вот, если они гомеоморфны, вот таким, вот давайте возьмем сейчас. Да, значит, из этого вытекает, что у нас есть we have maps from the disk to itself, H epsilon, which are the identity on an epsilon neighborhood of X. And that squeeze the diameter of the image is less than epsilon. So then we can define a map which is the limit of these epsilon for some sequence tending to 0. This is a map from the disk to itself. We also have the projection map, which takes and collapses the cellular set. It's a compact set, so it's fine. And then if we compose this is we get a homomorphism. And in fact, we can play the same game for a finite number of cellular sets. And so if we have two cellular sets, for example, x1, x2.
Sorry, why do you get a homomorphism? And why it is well defined even?
Okay, well, so you mean the limit? Or what?
Well, okay, perhaps the limit is well defined, but it need not be a homomorphism, right? This
Well,
G.
so it's injective everywhere apart from x. Do you agree? Because we chose it to be identity on every epsilon neighborhood of x, and the diameter of x is less than epsilon. Everywhere else, the h epsilon were injective. So in the limit, it's injective everywhere apart from x. But we collapse x in the quotient.
Sorry, I'm not getting then what are these h epsilon? I thought they are contractions in the preimage like you defined before. Is it like sigma epsilon? H epsilon is the same as sigma epsilon.
No, they're slightly different. So h epsilon is I extend by identity on either side. So instead of squeezing, I take, for example, some neighborhood here and I squeeze it, but everything else stays the same. So it's injective everywhere apart from x.
But why couldn't you have some point which is moved by each of them? I mean, h epsilon 1 moves it closer to that central point, and then h epsilon 2 moves it still closer, and so on. Why couldn't that happen?
So is the question, for example, that suppose we have a point here, which gets moved like close in and then keeps moving closer in.
Yes.
Well, I don't think this is a problem if we take epsilon to be very small. So for example, if we take epsilon I to be this, we can make so that we contract where it's the identity before. So
do you mean epsilon I equals epsilon I minus 1 over something? Over 2 maybe, no?
Yes.
Well, maybe that would still not be enough, because we probably want epsilon I to be smaller than so we have this squeezing, and epsilon I minus 1 tells us about the sort of upper diameter of what is squeezed. But then, I mean, in your picture, this big blue set is squeezed into the small blue set.
Yes.
And then epsilon, suppose for example, epsilon 0 could be the diameter of the big blue set. But then we want epsilon 1 to be smaller. We want epsilon 1 to be so small that the ball of radius epsilon 1 is contained in the small blue set,
Yes.
not just in the big blue set.
Yes, so this is, I think this is what I get by saying this condition, no? The second condition that I stated, that the diameter has to be less than epsilon. So then on the next one, it's the identity. So
I don't understand this condition. What is x? X is 1 point?
no, X is the set. Cellular is the set. Big X, it's a big X.
Where are these h epsilons live? Do they live in the domain or in the target?
No, the H epsilons are homomorphisms. Well, they're not homomorph. Yes. H epsilons are maps that are maps of the disk to itself, like the sigma epsilon, but they don't squeeze the whole image. They're slightly different. They squeeze stuff that's close to the boundary. So they're the identity on things close to the boundary, then they squeeze very hard, and the identity very close to X.
So do you first define some modification of the squeezing in the target of S?
Yes,
epsilon?
yes. So I said I extend by identity. So in the first one, I just said, well, we just squeeze very hard. And I don't care about what happens at the boundary. In this one, the modification is that I choose it so that it doesn't affect anything close to the boundary. And then I squeeze very hard. And then
So you first do it in the target, and then using that h epsilon in the target, you define h epsilon in the domain. Is that correct?
yes.
Okay. So now this condition, diameter h epsilon of x is less than epsilon. I don't understand. I would think that h epsilon is the identity on x. Isn't it the identity on x?
Yes, but it's, yes. Hang on. Then I think this condition is wrong. What I wrote is wrong. What did I mean?
May I ask, what are we trying to prove now?
I'm trying to show that if I collapse a cellular set, the quotient is homeomorphic. So we have the following proposition. So if X is a subset of the disk, is cellular, if and only if there's a map F from the disk to itself with X as its unique inverse set. So we showed one direction, that if it's the unique inverse set, then it's cellular. I'm trying to show the other direction, and that sorry. What is means? Sorry, that's not what I'm trying to show. I'm trying to show the following, that if I collapse a cellular set, X that's what I'm trying to show. But
How about this? Let us assume for simplicity that this map F is piecewise linear on the complement of X.
Sorry. Okay, I understand what I. Oh, sorry, I understand what I did wrong. Okay. So H epsilon is the identity on the complement of an epsilon neighborhood of X. And then this makes sense.
I still don't understand it. The diameter of X is not zero, probably.
Yes, but X got squeezed really hard, so that it's inside a ball of radius epsilon over 2. Well, so it's inside of a ball of radius epsilon. So on the right side, so we squeeze very hard so that X becomes really small. This satisfied the second condition. The first condition is satisfied by taking the radial squeeze to be the identity everywhere outside. We squeeze very, very hard, but we're still okay.
Then I again don't understand what is H epsilon. Maybe you could write the definition of H epsilon somehow. So you have the definition.
H epsilon looks exactly like, so H epsilon is basically sigma epsilon, apart from we complete identity, we complete by identity. So this rate, so okay, so S epsilon is a squeeze. So we have okay, this is the target ball, and this is the point Y. If we have a set here, so then my claim is that we can choose it to be the identity here. Then we squeeze very, very hard so that if we have a set somewhere here, then it will lie very, very within a ball of radius epsilon. And then we complete it to be the identity everywhere inside here.
This is S epsilon.
So this is just S epsilon.
and then sigma epsilon is obtained by conjugating as
Yes.
epsilon by F.
Yes, and taking the diagonal on X.
So then sigma epsilon is the identity on X, right?
Yes. Yes, sigma epsilon is the identity on X. Okay, that's something wrong. Okay. Could I maybe skip over this point and then, because I don't think I'll be able to finish in any case today, and I will, just so we don't spend too long, I will explain this next time, if it's okay with everyone.
Okay, maybe I can try to say some idea how this can be proved. Okay, let me try it quickly. Okay, Philip.
Yeah, sure.
So let's assume for simplicity that F is piecewise linear on the complement of X. Okay, to simplify matters. Then we have this this argument. Could you please go back to the previous picture with blue sets? Still yes, thank you. So we could do this argument with this white balls and blue balls being piecewise linear, and then their boundary spheres are piecewise linear, and the preimages of these boundary spheres are also piecewise linear. But then we can use the annulus theorem, which is easy to prove in the piecewise linear category. So if you have one PL ball inside of another PL ball, then their difference, the closure of the difference is an annulus. And you, because of this, we have annuli in the domain. So the domain consists of this preimage of that singular point, and also some annuli.
Sorry, could you repeat how you get the annuli? So you take a piecewise linear map, F is piecewise linear on outside X, yes?
Okay, so we take we can take this blue and white balls to be piecewise linear. Okay.
Okay.
Then we have a sequence of blue spheres in the target. Smaller and smaller blue spheres in the target.
Mm-hmm.
And between those spheres, we have annuli.
Yes.
And then in the domain, we have preimages of these blue spheres, which are again spheres. And between those spheres, we still have annuli. Because
spheres are balls. Spheres are balls.
Well, the preimages of spheres are spheres.
Yes. And
moreover, there are piecewise linear spheres. So because of that, between them, we have annuli. If we remove this X, the set X from the preimage, then the complement will be a sphere across the positive ray, 0, infinity. Because it is the union of this annuli.
Okay.
And then when we squeeze X to the point, we get a ball.
Yes.
So that's here we were assuming that F is piecewise linear on the complement of X, but then I think this shouldn't be really necessary because Well, okay. Yeah, okay. This I'm not able to explain well now. So I believe some modification of some very small modification of this argument would actually work without this hypothesis of piecewise linearity. And it seems like what you were trying to say is actually similar to that. But okay, this is just some idea of proof.
Okay. Yeah. Yeah. I'm sorry. I'll think through the details and I'll explain it better. But yeah, if it's okay with everyone, I'll move on. And if I can publish, I can publish it later in the notes or something. Okay. Yeah. So we have two. So we have squeezing it doesn't like still squeezing is quotienting by a cellular subset doesn't change the disk, and then the claim is that for if we have multiple subsets, then the same is true, and so that is if we have a map from dk to dk such that x1 and x2 are the unique inverse sets, then they're both cellular. And again, quotienting by them is still homeomorphic to the disk. So the idea is to consider this map. So if we consider, so if we just try to parameterize some neighborhoods of x1, well, we have this sigma epsilon, but this time it's not a homeomorphism because of x2. But notice that it's a map from the disk to itself with a unique inverse set. This time it's just x2. So by the previous proposition, x2 is cellular. So quotienting by it doesn't change anything. And similarly, we can play the same game for x1. Are there any questions? Okay, so then we can state the theorem, which was first proved by Maser, but we are stating Brown's proof, and which is that if Sn minus 1 admits a collar, that is an embedding in Sn, then the zero section is flat. That is that's a homeomorphism which takes it to the standard equator. So
in other words, you can say that it is tame and moreover unknotted.
Sorry?
This flat can be defined by saying that it is tame and also unknotted.
Okay.
Mhm.
So equivalent to something piecewise linear and unknotted. Okay, so well, we know that we have two components, A and B, and the idea is to realize them as the unique inverse sets. So they'll be cellular. So consider the quotient. If you're worried about what happens at the boundary, then I suggest, well, you just quotient by something slightly bigger than A. So we take, I don't know, we take from half and we quotient from there. I don't think this will change the argument. And well, what do we have in the quotient? The quotient is homeomorphic to Sn again, because well, it's a suspension over the zero section. And so then so then we just need to modify our theorem, our proposition slightly. So we talk about balls instead of spheres. And this can be done by excising a point or a small ball, and then in the image we again remove a point that's here. So if this is what, so then we have a map between balls with two unique inverse sets. Their quotients are still disks. So we have the following. And we have a further homeomorphism if we view this as a suspension, which takes this to the Sn, but here this time the zero section, I'll call it sigma, is taken to the standard embedded equator. So this composition is the flattening homeomorphism, and by the previous propositions, again we have this dA and dB, their closure are disks. Okay. I would yeah. So I wanted to talk. So there's an interesting question that was posed, which was a piercing segment. So suppose we have a sphere in R3. Then we would like to understand whether it's tame or not. And the following question was posed. So a piercing segment is a straight line segment according to the affine structure of R3 that intersects the sphere in exactly one point and has endpoints lying in different complementary domains. So for example, if this is just a standard sphere, this would be a piercing segment. And so the question was that is this enough to characterize tameness? So if a sphere can be pierced at each point, is it tame? And that the answer was no. I'll get to this. So there's I don't know. So there's a game called I don't know, pick up sticks. When we have a pile of sticks and we try to pick them up without making the ones above it topple. And there are certain constructions which where this is not possible. So we'll kind of view a following modification of this. So so suppose we have 2 planes, P1 and P2, and line segments between them such that the endpoints lie on different planes and the line segments don't intersect each other. So there was a question whether it's possible to individually move all these sticks so that they all lie in horizontal position and without intersecting each other. And so this was shown possible by Fox. So there's a family of homeomorphisms which straighten these arcs individually. And then Bing constructed an interesting example.
Sorry, how many segments do you have? Finitely many, countably many?
Can be the next example I will show uncountable will consist of an uncountable collection of segments as long as they don't intersect. So the next example I will show a Cantor set of segments.
So Fox proved for uncountably many segments.
Yes.
So the question is
to be honest, I'm not entirely sure. So Bing quoted Fox's result, and it wasn't specifically mentioned, but I assume that he proved it for the uncountable case because then Bing compares his result to Fox's and essentially says that the difference between his result is that this family of homeomorphisms doesn't extend to a homeomorphism of R3. So it was not explicitly stated that he proved it for an uncountable segment, but I assumed so because of what Bing said.
Anyhow, the task is to straighten all the segments while keeping the endpoints in the respective planes.
Yes.
Is that?
Yes.
Okay.
So Bing, and this was shown possible by Fox. So then Bing considered the following pile of segments. Pick 2 segments that are hooked in the following way. so this is the start construction. Oh, sorry, I skipped a step. So the very start is we just pick a V. So two segments which share the same endpoint here. And then what we do is we take a tubular neighborhood of this. And then inside this tubular neighborhood, we replace these segments by hooked V's, two copies of the initial stage. So I'll denote V1 to be this the union of two sticks with a shared endpoint, N1 to be the tubular neighborhood of this, V2 to be these two hooked segments, and N2 the tubular neighborhood, and so on. So the second stage looks like this. And then again, we take N2 to be tubular neighborhoods, which lie inside of N1. And then V3 to be each of these V's. We repeat the same process, so we will have 4. And so on, and Vn will be a 2 to the n V's. Let's use K.
Are they supposed to be linked in this picture?
Yes. That like this.
Okay.
I don't know. Is it clear?
Thank you. This is similar to the Alexander Horn sphere.
Yes, it's equivalent to the Horn sphere. It's equivalent to the Horn sphere. It's just drawn in such a way that it's very clear that well, yeah. So from this we can make a sphere. So the interesting thing was that so like I said, so even though there's a family of homomorphisms which straightens these sticks, then this curve J, we cannot move it in between P1 and P2, so that it lies above, because I mean it will intersect every n. So first I define the pile of sticks to be the intersection of these, and well, we cannot lift J without intersecting all of these, but it seems like we should be able to, because of this existence of a straightening homeomorphism, but it doesn't extend to all of R3. It was Bing's point, so that individually we can straighten these segments, but we can't. There's no homeomorphism of R3 to R3 which straightens these segments. So it's a sort of wild Cantor set of lines. And from this,
you're saying it does not extend to all of R3, but where is it defined, the straightening homeomorphism?
So the straightening homeomorphism is defined on the so the original task, which was straighten these segments individually, so that without like touching the ambient space, so that at the start, however they lie, in the end, they'll all straight. So
What
this
do
is a
you mean by-
homomorphism which is defined only on the family X.
What do you mean by individually? There is there one homomorphism or many homomorphisms?
Fox's method straightens each of the line segments.
I separate homomorphism.
I think it's the same on each one. I think it's something like you take you do it at the same time to all of them, and you take so if this is the start, then at point at time t, you move this segment so that it's so that its endpoint is the projection of the point that is ratio 1 over 1 to 1 over 1 minus t. So at this point, it will look like this. The segment will slightly protrude. I think that was his method, if I'm not mistaken.
If you apply Fox's theorem to this picture in the bottom, to this pile of sticks, what do you get? Are these segments going to intersect, or what happens?
To a finite approximation, or no?
Either way.
Is there a way to apply this to? I mean, these are not. This is not like the finite approximation is not a valid picture because they intersect. But if there's, but is your question that is that?
But they're supposed to be linked, right? Not they don't intersect.
Is your question is what if we apply Fox's to something like this?
Maybe in this case, it's clear how to straighten them, but in the previous picture, it's not clear what is going on.
But I mean, this is not a valid set of sticks because it's only valid in the limit.
Okay, because they have common endpoints.
Yeah.
Oh, I see. But okay, so what happens in the limit according to Fox? I mean, what was his claim?
Well, so I did not read Fox's original paper on this, so I don't know precisely what his claim, and I don't feel so I don't know what Fox's original claim was. I read Bing's commentary on what Fox said, and that was not very precise, so I can't answer that. But if I can try read what Fox said and then write something about it, if you like. Right. So so then from this pile of sticks, we want to make a sphere, and the idea is the following. So we have these two planes. And we choose a cube, which is which intersects in one face the lower plane, and then we protrude n1, half of the cylinder's n1, half of the n1 from here, and then n2, which was these linked ones. And so on, and until the limit. So this is equivalent to the Horn sphere. It's clear that every point on it, apart from the points lying in P2, can be pierced. So what about the points in P2? Well, they're pierced precisely by this pile of sticks X. So yeah, so this is a sphere which is wild yet pierced at every point. And I think being asked the question whether so it's no longer true if you ask the question, replace lines by pencils. So a pencil is like a cone, for example. So if you have a cone on either side, or he also asked about spheres, but I mean I don't know. Yeah, I don't know the answer to this either. I don't know. Maybe someone knows. Yeah, so I guess in some way this kind of tells us that we can't loosen this. We need the structure of the continuity of the collar in the Schoenflies theorem. We can't just take any segments. Yeah. Okay. So, yeah. So I guess if I have a little bit more time, if that's okay. So Cantarelli actually relaxed. It's possible to relax the Schoenflies theorem in dimensions greater or equal to 4. So a pinched collar is a quotient of so it's an embed. So a pinched collar at P is an embedding of this. V is in S1. So this is a pinched collar. It's an embedding of this in Sn. And for example, the Fox-Artin sphere that's wild in one point has a pinched collar. But Cantarelli says that actually this is the only example that exists. So in dimensions higher, such an example doesn't exist. I don't feel comfortable talking about why it's flat, but I can talk about some other stuff that he said. I don't know if So it seems that it relies on his proof relied on two things. So there's so there's arcs in Rn for n greater or equal to 4 that are a finite, that are a countable union of lines or segments and points are tame, are flat, sorry. And 2 was the Mazur-Swindle. So sometimes it's referred to the Eilenberg swindle. I have a seminar in 25 minutes. So I don't know if I'll be able to get through both of them. So which one would you like me to talk about? Okay, so sorry?
Maybe the first one?
Okay, yeah, I'll start with the first one. Okay, so the idea is the following. So we find a line that is parallel. So we find a line L that intersects the arc in one point, and any parallel translation of it will also intersect A in at most one point. Then using this, we find a homeomorphism of Rn to Rn, which takes A to some hyperplane. Which is...
Well, is A your arc?
Yes.
And in step 1, what is L?
It's a line, a straight line.
Okay.
Yeah, it's a straight line. So, I mean, we can see how if we find L, then H, it will just be moving so that every point on kind of projecting on each point along this line so that it lies in the hyperplane. And then 3 is that an arc that is tame in Rn minus 1, viewed as a subset of Rn, is tame in is arc in Rn is flat in Rn. So arc that is just an arc in Rn minus 1 is always flat in Rn. So the idea here we like the limiting case is kind of R3. So we want to project onto some 3-dimensional hyperplane if n is equal to 4. And then we go up again. So step 1. If we write A as a union of segments, then if we consider the set of lines that go through AN, so we take 1 point on AN and 1 point on AM, and we consider the set of lines that go through them. This is a 3-dimensional affine subspace. And the countable union of 3-dimensional subspaces cannot cover Rn for n greater or equal to 4 by bare category theorem, for example. So such a line exists. So then we can project kind of along it to some hyperplane, noticing that since each point was intersected exactly once, then A lies in some hyperplane. So from 1, we get 2. Okay, and for 3, we will need the following. So we will prove some slightly more general statement. So if alpha are and beta are embeddings of some compact metric space into Rm, then the embeddings alpha 0 and are equivalent to the diagonal. I.e. there's a homomorphism of Rn cross Rm that takes the image of alpha to the image of the diagonal map, and same for beta. Yeah. Okay, so we'll just show that alpha cross 0 is equivalent to this. Right, so so let us consider the map beta alpha inverse. This is a map from Rm to Rn. Or maybe I got the indices wrong. Yeah. And we can extend it by the universal extension property to a complete map between this. And then we define psi, which is now a map from I would like to notice that this is a homeomorphism with inverse the following. Okay, well, then this is what we want, because if we check well, this goes to because we define psi to be the extension of this map. And the beta case is very similar. So then we get the corollary. So an arc in Rn is flat in Rn plus 1. And this proves what we wanted. Right. I guess I'm maybe have time to talk about the other stuff as well. Right. So the next oh right. I thought it was maybe interesting. So what is an arc that is not a countable union of points and segments? So there's examples like an arc that contains a wild Cantor set, for example. So an arc on the Alexander sphere would satisfy such a criteria. But that arc lives in R3. So I guess we want some higher dimensional example. And I think the first person to do this modification was Blankenship. And then also, and then Brown a bit later, 1967, he actually found, I think, I'm not sure if it's Brown, but you can definitely find it in Rushing. I think it's example 2.6.6, which is it's an arc in Rn, so n greater than 4. Beta is an arc in Rn, which is wild everywhere but cellular. I mean, a point that's an arc that's wild everywhere is not a countable union of segments. But he has, it essentially uses the following, its construction uses the following theorem. I think it's due to Andrews and Curtis, which is that if Rn, so if A is an arc in Rn, then Rn quotient A can be viewed as a locally compact metric space by Urichon metrization. So then if we take its product with R, then this is homeomorphic to Rn plus 1. And a corollary, and the corollary of this, the idea in this proof was that to show that the following so this is equivalent to the following decomposition of Rn plus 1. And this is shrinkable I think that's how that was the proof. So a corollary of this was that
Sorry, do you assume that A is cellular?
I think it's let me check, but I think there were no assumptions on A. Yeah, I don't think. Yeah, definitely. I don't think so, because in Davidman Venema they use the like an arc on the Alexander sphere. No, sorry, an arc on the Antoine sphere, which is definitely not cellular.
Why is that decomposition shrinkable?
Oh, that's the theorem. That's what they proved. It's not trivial.
Ah, okay.
That's the theorem. That's what Andrews and Curtis proved. I think it was 1962 or something. Yeah, but it's also you can find the proof in Davidman Venema. I can't remember what section. It's like section 2, I think. But yeah, so using this here, we can construct arcs that are essentially everywhere. We can inductively construct arcs that are wild. The idea is that if we have an arc that's wild in, so we have alpha 3, which is wild in in S3, then we can define alpha n plus 1 to be the suspension of alpha n viewed as a subspace of which is and in brushing he shows that if the starting arc is yes, so I think I think the starting arc in rushing is some Fox-Artin arc. The suspension of this, or this iterative process, produces an everywhere wild arc that he also shows as cellular. But yeah, I did not read the proof of this, so yeah. But this is the method. This is the general method of construction.
What is the statement? If alpha n is wild, then alpha n plus 1 is wild, or some other statement?
No, I think it's some. Yeah, I don't want to say the statement in case I'm wrong, but I think it's another statement. I think it's what because I noticed that in Daveman Venema and in rushing they use two different arcs, but both of them end up being everywhere wild after this quotient process. So I think it's a bit more interesting. It's that possibly, I don't know, that irrespective of the starting arc, the arc that is obtained is everywhere wild. But I don't, again, like, I don't know about this. But yeah, so here this is a process of generating wild arcs. But yeah, that's not the, so yeah, that was a little bit of an aside. So back to Cantarelli, Cantarell. Cantarell uses a lemma, which is the following. So if Cn is an n simplex, that has a PL collar modulo 1 point, that has a PL embedding modulo 1 vertex, then the embedding, the image of the embedding is an n cell provided n is greater or equal to 4. So the idea is the following. So if we take the simplex, then inside it.
Sorry, do you mean that it is piecewise linear on the complement of a vertex?
Yes.
Okay.
Yes, that's exactly right. So if this is our simplex, then we can remove another simplex En from the interior and connect it via straight line segment alpha. And then we do a similar thing here. Except we take another simplex. So if the original simplex is K, yeah, so I saw it badly. So we have we have our original simplex Cn. We can consider it as a subsimplex of a larger simplex Kn, which shares the vertex that it's non-linear, non-piecewise linear. Then we can also consider inside Kn a simplex contained in its interior, which we call En, and an arc alpha, which connects V to some vertex of En. Right, and the idea is that, well, when we embed these, so each of these embed in the sphere.
But it seems we are given that only the small simplex is embedded. What was the statement? The statement said that Cn is embedded.
One second. Yes, the statement was that Cn is embedded, but the embedding is piecewise linear. I mean, yes, if we have Cn, which is well, we can extend this embedding of Cn to an embedding of Hn. So if E is an embedding of Cn into Sn, then we can, and Cn is a subsimplex of K, and then we can extend it to an embedding that's also piecewise linear modulo that vertex. So we extend it, and then the idea is to show that the following sets are homeomorphic. Yeah. So I'd like to note that this is a collar. So by the Schoenflies theorem, it's clear that F is an N cell. So now we would like to see why G is homeomorphic to F. And the idea was to use the previous proposition. So since the embedding is piecewise linear modulo one vertex, we can assume that the embedding of alpha is an arc that's countable a number of lines and segments, which is flat. So we can contract it. So then these are homeomorphic.
Why are they homeomorphic?
Well, alpha is flat.
Okay.
So there's a homeomorphism, which that's the identity on the boundary. Kn. Right, and it maps and it contracts alpha. It's like the endpoint of a pseudo-isotopy that contracts alpha. Its unique non-degenerate inverse set is alpha. And then we can extend this map via the identity everywhere else.
Okay.
So this gives us a map of Vicente itself. So we have a map. And it's non-degenerate. Sorry, H of alpha. And H of alpha is flat by the previous exercise. So there's a continuous map F again who's non and so then we take.
What is this F?
So F is the contraction of alpha, but the standard one. I actually had a question about this. So I don't know. Firstly, does everyone agree with this proposition?
I didn't understand the last step.
Okay, so do you agree that alpha is flat?
Okay, yes.
Okay, so if there's a self-homeomorphism taking it to a standard interval.
Mm-hmm.
Okay, and contracting a standard interval in Sn is still equivalent to Sn.
Okay.
Okay, so this is this map, which so G inverse has non-degenerate element alpha. Do you agree? This is I think it's very similar to how Fox and Artin kind of showed that the complement of the three cell was homeomorphic. We contract something and show that the complement was still homeomorphic.
You construct two homeomorphisms, two maps F and G, which both have just one non-degenerate point inverse, right?
Yes.
So their composition, this composition G inverse F, well, okay, it could be a homeomorphism, but what did we want to prove?
Oh, we wanted to prove that G is homeomorphic to F, because G, we know that F is an N cell. Sorry, the closure, the closures. But yeah, F is an N cell by the Schoenflies theorem, because this is a collar. The blue thing that I showed is a collar. And the idea is to contract this collar to get something, to get this picture. And this contraction, because the arc was flat, doesn't change anything. So outside it. And so then these are homomorphic. The proposition was that the complement of a simplex that's embedded PL modulo 1 point is an n cell. And we know that by the Schoenflies theorem, this is an n cell. And we would like to show that contracting the arc alpha doesn't change anything. So this is exactly. But actually, yeah, if it's okay, can I ask a question? Yeah, so because we had this theorem about this proposition about cellular sets, which was that the inverse, so a map from the disk to itself. I mean, like this is the same as this as well. There's a version which says this as well, which is one-to-one on the boundary and has a unique inverse set. Then I think there's a slight modification because obviously it's different for SK, but that has a unique inverse set, is cellular, and a cellular subset of Sn is characterized by the fact that its complement is homomorphic to Rn. So my question was that well, if we have an embedding of a disk or a simplex that's PL modulo 1 vertex, is there not a pseudo isotopy which takes that simplex to a point and is a homomorphism on the exterior? And so the endpoint of such a pseudo isotopy would seem to me like a cellular map which has a unique inverse set. And therefore it's cellular, and so its complement is an n cell, as an open n cell. But I didn't use anything about n is equal to 4.
What do you think?
Well, I was wondering whether there's some sort of problems when I take this pseudo isotopy, because I don't know, an embedding that's PL modulo 1 vertex, maybe it's not like, I don't know. But it seems to me like there shouldn't be a problem when I'm contracting, like if I'm repeatedly contracting simplices to a point. This is a question that I don't know the answer to. So I don't know. The idea is the following. So if we have an embedding of a disk or an n-simplex that's PL modulo 1 vertex, I propose to contract it in its ambient space. So if Dn is in Sn minus Sn, then there's a map of Sn to itself, which sends Dn to a point, and is a homomorphism on the complement. Now, if this map exists, it seems that it's a map with the cellular inverse Dn. So then so then Dn is cellular. So its complement is an n cell. but I didn't use anything about n greater or equal to 4.
Maybe some problem can happen if there is some kind of knotting. If
Yeah, that's what I was thinking about, but I couldn't construct an example.
so, for example, some wild. So this dn it is PL modulo one vertex. So it could be wild in that vertex, right?
Yes.
So in that case, the fundamental group of the complement could be non-trivial.
But I
And-
couldn't construct an example of that. I don't know, it seems to me that in general,
Well, if you just take infinitely many trefoils converging to a point, and then one more segment,
yeah,
this it's called wild or wild arc.
yeah, that's a wild arc, I agree.
So then the fundamental group of the complement is non-trivial. And if you have such a pseudo-isotopy, then the fundamental group of the complement to the point is trivial. So you cannot have such a pseudo-isotopy.
Okay. Okay, yeah, that makes sense. Wait, why is so it's wild, but so your claim is the trefoil knot, this infinite trefoil knot, its fundament and added one segment, its fundamental group is non-trivial.
Yes.
Okay. Okay, thank you. Yeah, then I agree. I'd still okay. Then I agree. Yes. So and the idea then like the final step in the proof is basically to I need to go, but I guess I'll just
Yeah. So maybe we anyway don't have time to finish everything. Yes. So maybe we postpone it.
Okay. Sure.
All right. Thank you very much. It was interesting.
Okay. I'll try finish there was a couple of points.
Yeah. So we continue next Wednesday, right?
Yes. All right. Thank you very much for listening.
Thank you, Philip.
Спасибо.
Thank you.
Okay. Goodbye, everybody.
Bye.